Good afternoon, everyone. Welcome to Taco Tuesday, commercial style. Brett Zerba here. I will be moderating today's event, and my very good friend Rich Medeiros will be the main presenter. A little kind of a different topic today, so we'll get into it shortly. But let me cover some ground rules here. Most of you already know what they are. It's 24 hours from the end of today's broadcast. You should receive an email with access to your PDH and the tape, or not tape, but the recording, because we are recording this for you. By the way, if you go to our website, you can review any of our Taco Tuesdays, both commercial and residential. They're all there, or the majority of them are there. Every time I use the word all, something bad happens, right? But most of them, if not all of them, are there. They're on a Taco's YouTube channel. This one won't be there. David says hello. So I have a feeling people are hearing me, but if some folks can raise their hand, anybody out there want to raise their hand so I know that, okay, I see some hands going up. Thank you very much, David. I appreciate that. So that's a good sign. Also today, there is a handout. You know what? We've been doing these webinars now, Taco Tuesdays, over 4 years. And it's taken this old guy that's yapping right now the whole time to figure out, why don't I put the presentation as a handout? Well, sometimes it takes a while for this old Polak to learn how to do things in advance. So anyways, today's presentation, Rich's PowerPoint, is available as a handout, and you can download that if you would like. So feel free in that regard. Taco, as you can see, we're celebrating our 104th year. Privately held company. John Hazen White is the current owner. It was his grandfather that started it in 1920. Good Lord.
1920.
That's almost when we were born, Rich. Just a couple years before that, I guess. After that, we were born.
But we were born when the Wright brothers flew the plane.
Yeah. Your two kids and my three kids were all born in the 90s, though. I mean, in the 1900s. Not the 2000s, right? My grandkids, though, were born in the 2000s. So it's kind of weird. Just think about it. I was able to, I live in Beverly, Massachusetts, which is near the coastline, north of Boston. And I sat out in my backyard and watched some of the eclipse yesterday afternoon. We got to about 94, 95%. It was pretty neat to see. My wife thought I was cuckoo, but nonetheless, it's not just because of the eclipse she thinks I'm cuckoo, but that was fun. Anyways, it was pretty neat for some of those places where it went pitch black. That was something else for 3 or 4 minutes. But anyways, other than that, I pretty much done yapping. So today's topic, what do we call it? Vertical turbine condenser water. Well, that's a new one on me, but I tell you, it's something to really consider as we move forward, as you move forward in designing, and there's some really good positives for thinking about going in this direction. And yes, Taco has a line of vertical turbine pumps, and there's other ones out there. I don't need to mention too many. There's plenty of them out there, but Taco does have a vertical turbine line. As a matter of fact, we just opened up. We just christened in February. What's that? God, what month is this now, Rich? We're in April.
This is April.
Yeah, so less than 2 months ago, it was towards the end of February, we opened up our new facility in Lubbock, Texas, for our vertical turbine.
How do you spell Lubbock?
I believe it's Lubbock, but I'm sure someone will type it in because there's a lot smarter spellers out there than me. But nonetheless, Lubbock, Texas, that's where our vertical turbine facility is. And one last thing, since I am a New Englander, 2 last things. I'm from Connecticut, big UConn Huskies fan, national champs for the second year in a row. And not that I like to brag, but I do like to brag. Talk about domination. They won the tournament last year, 6 games they had to win. They won the tournament this year, 6 games they had to win. All 12 of those games they won by double digits, by over double digits. I mean, Last year, they averaged 20-point victories in their 6 games. This year, they upped it to 23.3 points. Good Lord. God, domination, domination, little by little. And my friend Julio is saying it is spelled Lubbock. And then today in Boston, the Red Sox open up their home season against the Baltimore Orioles again in at 2:10. I'm not going
Is
to
that at Fenway?
It is at Fenway, Rich. It is at Fenway.
Well, where I am here in just south of Boston, it's bright and sunny out. So
Yeah.
hopefully they have good weather for the opening game.
Yeah, they say it's very nice at the beginning. It is going to cool off, right? They're starting at 2:10, so game shouldn't end till around 4:30, 5 o'clock, 5:30. So by then it'll get a little cooler. But for April in New England, it's not a bad day whatsoever. But you know what? I am done talking. Go Orioles, David. David, I can't see his last name, is saying go Orioles. Yeah, the defending AL East champs. Hopefully they don't go one and done if they win again. Hopefully they don't go one and done. Not that I don't remember. Go Orioles, go Sox, go everybody. All right, Rich, I'm done yapping. Let's have some fun. I will be monitoring the questions. Rich Medeiros, take it away.
Well, thanks, Brett, and welcome everyone to today's discussion. I have a kind of a cryptic title. I put down vertical turbine condenser water. What I'm really talking about here are vertical turbine pumps used in condenser water systems, and specifically, very specifically, whenever we have a condenser water system that has an open cell cooling tower. So what are some of the things we're going to touch base on today? Well, first of all, I have to press enough buttons to get this to do its thing, Brett. Let's see if we try this one more. There it goes.
All right, we're going, baby.
I know, I'm on a roll now, right? So we're going to talk about the net positive suction head review. And so this is kind of an extension of our previous discussion 2 weeks ago on net positive suction head. But we're going to do a very short review so that everyone's on the same page. We won't go into the same level of depth that we did on the NPSH discussion 2 weeks ago, but we'll cover enough so that people that were not involved with that discussion will know what's going on. Okay, so what are we talking about? Condenser water systems, and again, repeating open cell cooling towers, open cell cooling towers. And we'll talk about that in some detail. And then the cooling tower height and its relationship to NPSH, net positive suction head. We'll talk about a conventional pumping system. And then, of course, the main topic today is vertical turbine pumps. We'll talk about those, and then we'll have a discussion at the end. Now, today's discussion is not all that long, but hopefully we'll generate enough. We'll create enough information to generate questions out there, and that's what our hope is today. So let's go through the NPSH review. So here is a little diagram of a cooling tower, and I'm going to start with my magic pen, Brett, and hopefully you can see this. It works okay.
I can see a red. I can see a red. There it is.
There it is, a red arrow. So there is the open cell cooling tower, just as the name implies right here at the top. What that means is that the water level, if I can just kind of make a squiggly line here, representing the water level in the cooling tower. That's not the straightest line in the world, is it, Brett?
Well, you said squiggly, so it's squiggly.
It's
squiggly. Water's very rarely flat.
Yeah, it's open to the atmosphere, which means that if I open the door of this cooling tower and looked inside, I would see this tank. And for today's discussion, by the way, we are going to assume we are at sea level. Sea level. That's kind of important.
As the crow flies, I'm about a mile to a mile and a half from the sea. How about you?
Yeah, actually, I'm just about the same distance, about a mile and a half. Yeah. If I go due east from where I am right now, I would fall into the, well, it's kind of not exactly, it's not exactly the Atlantic Ocean, but by virtue of the fact that it's a bay, I live in the town of Duxbury, and it's Duxbury Bay, and Duxbury Bay is connected to Cape Cod Bay. Cape Cod Bay is open to the Atlantic Ocean, so it's all one body of water. So anyway, the water level in our cooling tower, and this little example that we have here for a diagram, we're showing that the center line of the pump, and I'm let me see if I can draw a little arrow here pointing to the center line of the pump. On the suction side of the pump, the elevation difference between the water in the tank and the center line of the pump is 2 feet. So when we want to figure out what the net positive suction head available in the system, hold on one second. You're not going to believe this, Brett. I got a dog hair floating on my screen here. That's never good. Okay, so the elevation difference between the center line of the pump, the suction side of the pump, and the water level in the open cell cooling tower, and our simple example here is 2 feet. And if we want to calculate what is known as the net positive suction head available, we have to follow this little equation up here. And we always want the available pressure to be greater than the required pressure by the pump. That's why I circled over here. Net positive suction head available is greater than the net positive suction head required by the pump. And I define those two terms up in the top of the screen right here. Look at all those handy dandy little arrows and stuff. Isn't that cool?
It is. It is. It's very good. I
So
want
I'm going,
I want the audience to realize if you download the handout, you don't see the arrows. So just
you
keep
don't
that
see
in
the
mind.
arrows.
This is bonus coverage right here. These arrows.
Do you remember the song "Me and My Arrow"?
I do.
Really? Wow, you and I are about the only ones that remember that. Let's see if this will advance to the next slide here.
It did.
How to find the net positive suction head required by a pump. Well, it turns out you get that from the manufacturer's published performance data, and in one case, it's right on the pump curve. So this particular pump has a design operating point of 2,400 gallons per minute. That's GPM. GPM. And you can see that. Let me put a little tick mark down here on the graph. So I made that tick mark along the bottom here where it says flow in gallons per minute. And the pressure for this is at 125 feet. That's the design operating point. So there's the 125 feet. Well, let me put a little arrow there so you can see that. There's 125. Where those 2 points intersect, that's what the red dot is. So it kind of put a little cloud around the red dot. Well, if you follow that 2,400 gallons per minute vertically upward, you can see there's another graph up here that says required net positive suction head. And this is what's required by the pump. So if I follow that line vertically upward, you can see it intersects here. And when it makes that intersecting point, it's approximately the net positive suction head, NPSH, required by the pump, in this case, is 26 feet. You should be able to read that. So where do you get the information, or how do you find it? It's on the manufacturer's data. All pump manufacturers publish their net positive suction head required by the pump. And for TACO, it's quite easy to find because it's always on the top of the graph over here. Okay, so this again is a quick review. Any questions, Brett, before we go on to a little bit more?
We have a statement from Chet. Listening to you guys is like listening to Bob and Doug McKenzie.
Who is Bob and Doug McKenzie?
I don't know. I got to Google that. I don't know who that is. I don't know.
Well, maybe the person that
I hope it's a positive thing and not a negative thing.
Yeah, I know it. You never know.
Boy. Anyways, that's the only comment/question so far.
Okay. So we're going to go back to our diagram one more time. And this time we're going to substitute some numbers into the formula. So here's the formula at the top of the page over here. And the terms, I've defined the terms. So the first term is called the atmospheric head or atmospheric pressure, then the vertical distance, the friction loss, the velocity head, and the vapor pressure. Well, it turns out based on the temperature of the water. Now this is just plain water, and it's the water in this case is defined by the Hydraulic Institute as clear water. And I've said this several times. Actually, let me go back to the pump curve. If you'll notice in the lower left-hand corner, it says these curves are based on clear water with a specific gravity of 1.0, and that's defined by the Hydraulic Institute. And just as a quick reminder, the Hydraulic Institute is the organization that sets the standard for pump performance testing. So all of our pumps are tested in accordance with the Hydraulic Institute standard 14.6. 14.6. Okay. So what we really want to focus on today is we're going to look at the big picture. I'm going to erase my little bubble here for a second. Let's see, put it over there and erase that. The atmospheric pressure, and since we're at sea level, that's fixed based on the elevation above the Earth's surface, above sea level rather, I'm sorry. So since we are at sea level, this is what we're saying, we're at sea level, the atmospheric pressure is approximately, I'll write it over here, 14.7 pounds per square inch absolute. And in feet of head, it winds up being approximately 33.9 feet. And then the second term is the vertical distance between the water level, and that's what that tank came out to be. So between the water level in the tank and the center line of the pump, in this case, it's 2 feet on this little diagram. Now, the reason we have a plus and a minus in front of that term is because if the pump was located up here somewhere, for example, it would have an elevation above the water level in the tank. So whenever the distance is, the pump is above there, it winds up being minus. So in this case, it might be minus 2 feet. Now, we do not recommend, which is why I put a big X through here, we do not recommend that you put the pump above the water level in the tank. But for purposes of the equation, we have to designate whether it's a positive or negative value. And that's why we put that up there. So the first term, again, one more time, that's the atmospheric pressure. The last term is the vapor pressure. And so the only 3 terms that we can fiddle with is the vertical distance, the pressure drop in the piping system, and the velocity head. And if you recall from last week, 2 weeks ago, we calculated the velocity head, and we said the velocity head, which is this guy right here, is v squared over 2g, and if the velocity is approximately 8 feet per second, then the velocity head is going to be approximately equal to 1 foot. And so most people actually ignore that value because it's a very tiny value. All right, so we're only interested in today in these, we need to know about all 5 terms, but since we're interested in seeing what the effect is going to be on the other terms. So I'm going to go to the next picture, and I believe in the next one I have the arithmetic added in here. Yep, there it is. So I've repeated the formula and I put in the values. You can see 33.9 feet, that's atmospheric pressure, plus 2 feet. Remember, the pump is below the water level. The center line of the pump is below the water level in the tank. So that's plus 2 feet. So I got the first term, a little check mark on top of the feet here. Got the second term. The third term is the pressure drop in the piping system. That means that the pressure drop, here's a straight run of pipe right there. There's an elbow. There's another elbow. We also have an isolation valve, a strainer. When they did the calculation for the pressure drop for the fluid flowing through this piping system, it came out to 20 feet. So that's where that term came from. And then, whoops, what happened here? We got an interruption from the outside world. And we just said a minute ago that the velocity pressure, velocity head, is approximately 1 foot in this case. And then the vapor pressure is 2.2 feet. And where do we get that value? We get that from the steam tables. And I think I have a copy of the steam tables. Let me just see if I do here. Did I include a copy of the steam tables? No, I did not. Well, if someone wants to know where I get that value, I'll show you where it was at the end of this discussion. So when we add and subtract all those numbers together, we get the net positive suction head available for this particular system as 12.7 feet. All right, so let me just erase all of these things here and just kind of re-emphasize that we're at 12.7 feet.
So Bob and Doug McKenzie were fictional Canadian stereotype of Canadians characters and they speak in exaggerated accents, ending almost every sentence in eh, uh,
Eh?
and living on a diet of beer, bacon, back bacon, and donuts.
Well, I can identify with the donuts, eh?
Eh? And
Eh?
then
Well,
Daniel
in
and William.
Canada, they don't, I don't think they have many, if they have any at all, Dunkin' Donuts. I think they have Tim Hortons in
Yeah,
Canada.
it was a net positive comment. He said, "That's good, Chet."
That's a good.
Daniel and William think we sound like the Car Talk guys. Tom and
Oh
Ray
yeah, like Click and Clack.
Maglianozzi, Boston boys, NPR
Yeah.
radio, I guess. Anyways, back to reality.
Back to so in this little diagram, this little system, the net positive suction, has circle it one more time, is equal to approximately 12.7 feet. Now, if you remember a few slides ago, well, let's just go back quickly to those other slides here. If we go back, we said that the net positive suction head required by this pump was 26 feet. That's this value right over here on the chart, 26 feet. All right. So let's go back to our calculation. We calculated the available pressure is 12.7 feet, and we said that the pump requires 26 feet. We have a problem. So I put a little warning sign here. This is dangerous. You do not want to do this because, as we explained a couple of weeks ago, if the available pressure is less than the required pressure, the pump will cavitate. It'll make all kinds of noise. Sounds like it's pumping rocks or marbles. Some people say ball bearings. And it could vibrate. It could actually, in very, very severe cavitation pumps, it will actually shake on the whether it's connected to the housekeeping pad or the inertia base. So it's a major problem.
I think one of the reasons why we're seeing that 2 feet, that the big that value right there, is because more and more systems we're seeing, I think maybe some of you folks are seeing, is the tower is going on grade. It's not going on top of the building anymore. You know what I mean? It's being hidden down low, and all of a sudden you just can't get that differential height that you need so much.
Right. So part of today's discussions is a bit interactive. We're going to ask the question, we have a problem. In this particular system, let's assume that it's already designed, it's ready to be built. And the question we're going to ask our audience out there is, what would you recommend for a solution? All right, so while you're thinking about that, you can type it into is that called the question area, Brett?
It is.
Yeah, so type that in, and while I'm chatting here, how can we solve this problem? And while you're thinking about that, I'm going to continue with my discussion.
Well, James said, lower the pump level, enlarge the pipe size, or raise the tower. And Edwin said, change the pump selection.
Those are all good solutions.
Use different pump selection.
Yeah.
Steve is jumping right to the title of the presentation. Reduce HF.
So let's go through. So since we got some great answers out there, let's go through the first one. The first one is to raise the cooling tower. So here's a cooling tower. I'm going to point an arrow up and just say that I'm going to raise the cooling tower. And this is kind of a gross picture here, but you get the general idea. So there's the cooling tower. If I raise that cooling tower up, now look at what do I need to do? I need to make my available pressure to be roughly 35 feet. If the pump requires 26 feet, I'd like to be 10 feet above that, which means that I'd have to add, if you will, roughly 18 feet. That means I'd have to add 18 feet. I have to put that cooling tower an additional 18 feet. If I add 18 to 12, that's 30.7. So that's roughly, well, let's say maybe a little bit taller than that, right, Brett?
Yep.
If I wanted that to be 35, that means I'd have to add about 23 feet. So let me X out my 18, approximately 23 feet. And now that's a lot of structure, and that's a that's a tower that's way up in the air. But that's one way in solving the problem. The second way to solve the problem is to reduce the pressure drop in the piping system. And I think someone mentioned that, increase the pipe size.
Quite a few people.
Yeah. Well, that may or may not be a good solution, partly because in any piping system, you might be selecting the pipe at somewhere between 8 to 10 feet per second. Well, if you want to reduce the pressure drop, you'd have to significantly increase the pipe size, and that could create a whole series of issues which you may not want to get involved with.
Yes,
And the other,
Brian suggested raising the height will add a substantial steel frame cost plus screen wall cost, as most jurisdictions require screening. I'm
yes,
sure. I'm sure some type
that's
of,
right.
yeah, yeah.
I can remember in my career designing systems, we were working for an owner and an architect way back in those days. And they wanted screens around the cooling tower. They did not want to see that cooling tower. And they actually had the architect draw up some line of sight drawings to show how tall the screening would have to be around the cooling tower in order so that you could not see it from the ground. So anyway, yeah, it's a big deal. And then the other option that someone said, we could replace the pump. Yes, and let's assume for a moment that that was not an option for us, but we're going to talk about that in a second. Well, when I say replace the pump, I'm talking about replacing the pump with a conventional pump, which in this case is a KS pump, KS, which is a vertical turbine, is a vertical inline, which is split coupled vertical inline. That's the model pump we have, KS, which stands for vertical inline split coupled. Okay,
Now,
let's assume.
Rich, George says add pressure tank on the pump suction side. Is that, I don't remember that ever coming up in any of our conversations.
No, we cannot do that. This is an open system. If you add a pressure tank to the suction, all you're going to do is overflow the cooling tower because it's open to the atmosphere. And if you add pressure to the suction side of the pump, it's just going to push the water out of the cooling tower and spill all over the place. So you can't do that. That would be true of a closed loop pressurized system, but today's discussion is about open cell cooling towers and specifically the problems that we have with elevation and not positive suction head available. Okay, so let's continue on here. These are all potential solutions, but they may not be the most elegant solution. Let's go to, I just have a photograph in here of what a impeller looks like when it's been cavitating. So if you don't solve the problem in terms of either elevating the tower, changing out the pump, or lowering the pump with some other solution, you're going to wind up with a very bad impeller, and that impeller is going to die within just a few weeks of severely cavitating. It's just going to destroy itself. Okay. So here is a vertical turbine pump curve, and it has a similar information. This is 2,400 gallons per minute, so I'll write that up here. Just like the conventional KS pump, this is 2,400 gallons per minute, all right, at 125 feet. And in this particular selection, you can see, you may not see the lettering, it might be too small, Brett, but I'm going to circle it anyway. It's down in the lower right-hand corner, and the net positive suction head required by this pump is approximately equal to 20.9 feet, 20.9 feet. And if I plot my 2,400, let's say I draw a vertical line up here to the NPSH required curve at the top, you can see it intersects that line roughly there. And you can see that's a little bit less than halfway. Well, this is 15 feet over here, and this is 30 feet. So the increments between these 2 points is 15. So it's slightly greater than halfway. So halfway is 7.5. It's roughly 8. 8 and 15 is roughly 20. Yes, it's roughly, it's a little less. I'm sorry, it's a little less than halfway. So it's somewhere in the range of around 20 to 21 feet. And the software has told us here in the lower right-hand corner that it's 20.9 feet. Okay, so now let's look at what we might do. So one solution would be to put in a vertical turbine. This is a very special vertical turbine. It's called a vertical turbine canned pump, and it has a can at the bottom. It's pre-configured in such a way that all you have to do is drop it into an opening, and I'll show you what that looks like in a minute. That drops the suction of this impeller. In this case, let's say that that suction line gives us a new elevation of 30 feet. That means that our new net positive suction head available is 40.7 feet. Now, suddenly, with the net positive suction head required by the pump of 20 feet, that gives us more than enough distance so that the pump will not cavitate. So I'm kind of exaggerating the numbers here just to give you a quick feel of what this might look like. So all we did on our original diagram was substitute a vertical turbine canned pump, and I'll write the term canned down here, A-N-N-E-D, canned pump. It's a vertical turbine canned pump. And the beauty of this pump is that it has very similar connections to a vertical inline. It has the suction over here, the discharge over here. But what you don't see below ground is that it has a can, and then the pump impeller, or bowls as they're called. Well, actually they're called impellers with bowls around them. The elevation is dropped. So now instead of having only 2 feet, we now have 30 feet. Okay. And if I go to another diagram, so that's when the cooling tower was at some reasonable level, all right? So here's another diagram where I show the cooling tower almost sitting on grades. See that? Let's go back and forth between these two. Actually, let me erase these numbers here. Erase all of that. So here's my cooling tower. This is the original over here. And then the next diagram shows it at a lower elevation. So now my distance between the water level and the cooling tower is 20 feet, and that's on the suction side of the pump. So now this is kind of an ideal case. The available pressure is approximately 31 feet, and the required pressure is approximately 21 feet. So that's a 10-foot difference, 10 foot. So you don't have to go to 10 feet. I like to try to make it 10 feet so that it's not going to give us any problems at all. And look at what we've done. We put in a vertical turbine canned pump. It's all pre-configured. It's got the motor, it's got the inlet and the outlet and the pump and the shaft and the column and all of that stuff all in one simple package. And all you have to do is create a place to mount this pump, say perhaps on a concrete pad. Obviously, you have to drill a hole. In this particular case, the can is somewhere around 36 inches, and that's well within the range of most any industrial auger can just drill down. So if you have a concrete pad, you can just mount this pump. And so it makes it, you've solved all your problems. You've got the cooling tower at a lower elevation, you've got the net positive suction head available much higher than what you need for the pump by at least 10 feet, and you've solved a couple of problems. And sure, a vertical turbine pump compared to a vertical inline pump is a little bit more expensive, but look at how much steel you're going to save and how much piping you're going to save on the suction side of the pump. So to go to a vertical turbine for a condenser water system has a major advantage whenever the cooling tower elevation and or piping is not configured to give you the best net positive suction head available. And so what you wind up doing is putting the cooling tower up quite high, or you increase the pipe size, all of these things that will have a gigantic increase in cost. And for just a small incremental increase in cost for the pump, you've solved all of your problems, including the cooling tower is now at a very low elevation, including the cost of putting screening around the cooling tower. So this becomes a real elegant solution. So before I go any farther, do we have any questions out there?
We do. So there's some really good questions here. You kind of answered one, but I want to emphasize the answer. So is a portion of that pump down in a pit?
Well, let's put it this way. You have to drill a hole. So the hole would be, so here's the can. The can is part of the pump assembly. So you have to drill a hole, if you will, so the can fit inside that hole. And again, you know, if the can was somewhere around 24 to 40 to 36 inches, let's put that in there, 24 to 36 inches, that's a fairly simple hole to drill with a conventional auger. So mounting the pump is quite simple. Hopefully that answered that question for someone.
Yeah. Is so if you go back one spot, I think it says, is the pump really 30 feet tall? I think these vary, right, in height, but it can be. But,
Well, actually, in this example, the pump is probably only about 8 foot tall when you consider
well, the
above
other
the
sketch,
can.
the other sketch you showed 30 feet.
Yeah, you
When
have
you,
to keep in mind that this
yeah,
is that's the elevation
right.
between the. Yeah, it could be 30 feet for the whole for the height of the pump.
But
I'll
more than
show you a
likely
couple
it's
more
less than that.
pictures,
Yeah.
but in most cases, it's going to be less than that. Yeah.
Yep. Is there a pressure drop associated with the can? Is that included on the data sheet from the pump selection?
Well, actually, again, the net positive suction head required by the pump is at the inlet of the pump. So it would be down here, would be at the inlet. And we give the information, if you notice the suction side of the pump is larger than the discharge. And that's designed so that the water will enter the can and flow down between the suction connection and the inlet of the pump so that the pressure drop is negligible. It's specifically designed that way so that there's virtually no pressure drop between those 2 points.
And then Julio says, does TACO provide the can? And the answer, you already answered that, correct. Yeah, it comes with
Yes,
the,
it's a
it's built into the
pre-configured
pump.
assembly. I have a couple of pictures I'm going to show you in a moment. But yes, it comes as a complete package. In fact, do I have, is that what's next here? Yeah, okay, here it is here.
Well,
So
let me
here
ask,
is,
before you get into this, a couple more questions. How does this pump get serviced? Well, you know, you'd have to look at the weight, and obviously you got to pull it up with a crane or some way like that. That's probably the best answer, wouldn't you say?
yeah, I mean, the way this is, so let's go through the little diagram first here. So on the
Yep.
left side, just kind of draw a quick bubble around this here. This is a conventional system. This is what we showed earlier, which would be a typical KS pump. And in that case, the cooling tower, you may have to raise the cooling tower up in the air in order to get the net positive suction head available high enough so it is greater than what's required by the pump. And as I said, in a vertical turbine, this is the next little kind of clouded area here. In a vertical turbine, now you can lower the cooling tower. You can make it as low as you want. There's a practical limit because most cooling towers have the piping connected underneath. Not all the time, but it can be connected underneath. So maybe it's off high enough off the off grade or a concrete pad to ensure that they have enough room to connect the piping. But the point is that you can have the cooling tower at a minimum height. So all of the steel, you're trading off the cost of the steel and the cost of the piping, the vertical piping. So let me kind of erase that so it's get a little crowded here. So you're going to save on the steel, which is the 2 black lines. You're going to save on the piping, on both the supply and return piping, and any fencing or what was that other word we used a few minutes ago around the cooling tower? Some kind of
Screening.
screening. Yeah, the screening. So so you save on structure, pipe, and screening. And the cost difference is the small incremental difference between the KS pump and the vertical turbine pump. And like my little kind of sketch here shows, is that here's the picture I showed on the previous diagram. You get a little bit better picture. So here's the can down here. I'll put just the letter can here. And here's the electric motors at the top. So for general service, you lift the whole, you disconnect it from the piping system and you lift the whole thing up out of the can, but the can stays in the ground. And then you can see on the right-hand side, kind of almost a 3D version of that. And you can see this is the poured concrete pad here, all right? And then the can fits inside that concrete pad, and then the pump bolts right onto the can so that the installation becomes very, very simple. And that's how you utilize a vertical turbine pump.
I think our goal, your goal, was to show one method, in our minds, in many minds, the easiest method to do this. But there are other types of vertical turbine pumps. There's quite a few other types, and there's other ways this can be done. But this does look like maybe the simplest way and less expensive way to do it.
Yeah, one of the benefits of this strategy is that the installation has been dramatically simplified. And once you set up the concrete pad with the opening in it, and you've drilled through that opening, usually the ground. So the brown area here, this is the dirt, if you will, or the ground itself. And then the gray area is the concrete pad. And the concrete pad is poured in such a way that the pump fits right on top of that concrete pad. And it makes the installation super simple.
And we do have some other comments / questions. So the vertical turbine pump, and this is pretty true, is really only for applications where the cooling tower is on grade and the same elevation as the chiller and the pump and the can. I mean, we're seeing more and more of that, but that's probably the case, wouldn't you say, Rich? I mean, if the cooling tower, open cell tower, is up on the roof and you're down in the basement, or where the pump is, more than likely you wouldn't need this type of setup, correct?
Yeah, I mean, in the last couple of years, the net positive suction head available, people have not been doing the calculation properly, and we've seen all kinds of problems. And the major issue is that they're restricted by one reason or another, so that the cooling tower sits on grade, and there's not enough available pressure to keep the pump from cavitating. So this solves that problem, and we're seeing more and more designs where the cooling towers are sitting on grade. Now, if you put a cooling tower on the top of a building, you have to carry the weight of the cooling tower through the structure of the building. So there is some cost associated with that. But yeah, this is an elegant solution. If the cooling tower happens to be sitting up on structural steel, and that structural steel is 20 feet in the air, probably get away with a conventional vertical inline, like the KS pump that we show over here on the left-hand side. But more often than not, the cooling tower wants to sit as low as possible. They want the least amount of screening around the tower, and a vertical turbine is an elegant solution for these kinds of problems.
And then is 36-inch depth pretty typical for a vertical turbine can pump, or can you go deeper?
Not 36 inches is not the depth. It's the anywhere from 24 to 36 inches for the can itself. So
Yeah.
you would adjust the depth of the vertical turbine. So this piece right here, you can lengthen this piece so that you can have a lower suction elevation relative to the water. So you have to do the calculation, and so maybe in some cases the distance, as I'm showing here, maybe this is 10 feet. All right. And in other cases, it might have to be 20 feet or something different. It all depends on the system. One of the things that we said was someone said it, which was correct. What about changing the size of the condenser water pipe? Will that reduce the friction? And the answer is yes. But in some cases, the pipe is quite long. I was on a project, it was actually about 3 months ago now. And the distance between the cooling tower and the suction side of the pump, the horizontal distance that the pipe ran, was over 1,000 feet. So yeah, there's all kinds of crazy things that are happening out there. So in that case, the pressure drop would be significant, in which case you'd have to have a deeper can so that you could have enough pressure available for the pump.
The vertical turbine pumps can go a lot deeper than 3 feet, 2 feet, 3 feet. That's for sure. I mean.
Oh yeah,
Yeah,
actually they can go over 1,000 feet.
Yeah.
But for cooling tower applications, they don't have to go that deep. I mean,
no.
generally, you're going to solve most of your problems somewhere between the bottom of the can and the concrete pad is going to be somewhere between 10 to 20 feet, and that's going to solve the overwhelming majority of problems out there. But there could be an isolated case like I ran into a few months ago where they had over 1,000 feet of pipe, and
Right.
in order to get it to work, they would have had to put in vertical turbine, vertical turbine that was down around 40 or 50 feet.
We do have a couple other great comments slash questions. But before I get into them, vertical turbines in our industry, HVAC, aren't as prevalent as they are in many other industries, mining, farming, wastewater treatment. That's probably where they're more applicable for many applications. I mean, I've driven through farmland in California, and you'll see a row of, it looks like motors just sticking up and there are vertical turbine pumps, so this is kind of a smaller application that's pretty simple for this type of application.
Well, the other advantage is that these pumps are designed, can be designed, and the ones we're looking at today are designed to sit out in the weather, which
Right.
means that not only do you save on structural steel, on piping, on screening, but also if you put it outside the mechanical room, you save on mechanical room space because these pumps are designed to sit out in the weather.
Yep.
And and whenever you can save real estate. So look at all the things you're saving to help offset the cost of the pump. You're saving on structural steel, you're saving on pipe, you're saving on screening, and you're saving on real estate inside the mechanical room, especially if you had a much larger system where you had perhaps somewhere around, say, 4 or 5 cooling towers, and you would need to have maybe 4 or 5 pumps. That takes up a lot of space inside your mechanical room.
A couple of people asked this question, so I want to bring it up, and I'm anxious to hear the answer. Can you go back to your original before that, the one that just shows the KS pump. So a couple of people asked, what if you add a second pump? How does that work? Does that help?
Well,
in
yeah,
series?
that's a possibility. Now, are they talking about putting pumps in series?
Yes.
Well, that wouldn't help because the problem with putting the pumps in series is that the pressure drop is driven by the elevation difference between the water level inside the cooling tower and the center line of the pump and the amount of piping in the system. So you could actually, if you put pumps in series, it's possible, not necessarily all the time, but it's possible to have 2 pumps that are operating or that are cavitating if you put them in series with each other, because the velocity of the fluid hasn't changed.
Right.
Now you could put pumps parallel to each other, but now you're buying, in both cases, by the way, whether you put them in series or whether you put them in parallel, you're buying more pumps than what you need. So if you had 4 cooling towers, now you have, say, 8 pumps per cooling tower. I'm sorry, 4 cooling towers, 8 pumps total, or 2 per tower.
We do sell pumps, so that's not necessarily a bad thing. But
well,
you know what though, we always profess keep it simple. Keep it simple.
Right.
So
do we have any other questions?
Daniels made an observation. If the height of the tower remains a challenge, you can install the tower without a sump on a concrete sump below grade and install vertical turbine pumps on the sump, which would generally only have the pump motor protrude from the surface of the sump.
That's absolutely correct. And as it turns out, many larger chiller plants use that exact approach. They will build what is known as a concrete vault, and they'll sit the cooling tower on top of the concrete vault, and the vault becomes a big tank, concrete tank. And the cooling tower drains into the tank, and then the vertical turbine is mounted on the top of the tank. And that is fairly common for very, very large systems. But I'm talking about systems that are probably in the sweet spot of commercial HVAC. It's probably somewhere between, I don't know, 1,000 and 1,500 tons. And that order of magnitude, the cost of building a concrete vault would be a huge penalty. But to drill a simple hole and mount the vertical turbine on a concrete pad outside in the weather is really simple. There's nothing to it. If it's a canned pump, you don't have to worry about debris coming in from the concrete vault or any of those other issues. So yeah, it's a real simple element.
Can you scoot ahead a little bit on your things? I think there's a couple. Yeah, this picture here. Um, is this pump supported by the flange on the ground? Well, if you kind of look on the right, you can kind of see how that's being supported, right?
Well, it depends. It turns out, I checked this with our engineering group. It depends on the final design, which has to do with the diameter of the can and the length of the can. So in some cases, they may have to have some grout put in to stabilize the end of the can. In other cases, because it's relatively short and narrow, you don't need anything. So it's really quite simple.
Michael's asking, what is the can material?
In most cases, it's steel.
Yep.
And it can be coated with a, there is a technical name for it. I'll just call it black tar. That's not the technical name for it, but you can coat it on the outside of it. That makes the can last almost indefinitely.
I mean, you already covered this. Someone's asking again how you service this pump. I mean, you got to lift it up.
Yeah, you just pull it up vertically. Usually there's an eye on the top of the pump. So in other words, there would be an eye hook up here. And then you would just lift the whole thing. The can stays in. After the initial installation, the can stays in. And you just pull the whole pump up. You don't have to pull anything up to remove the motor other than the motor is bolted on top of this section here. And you can lift the motor up, but you don't have to take the whole pump apart to get the motor up.
I mean, someone's asking, what if you make a really, really big pit so you can service it below grade? But I don't think that's as practical as it should be, because then that's all going to be fit. Yeah, that's it's still inside the can.
Yeah, I mean, this is a very,
Right.
a very specific application. This pump is designed this way to work, to be a very simple installation, to solve the problem with cooling towers that want to sit on grade. And the cost is dramatically offset. The savings in pipe structure and screening, and perhaps even mechanical room space, which you need to include all four, is that penalty is much, much greater than what your cost would be for the differential cost between a KS and a vertical turbine pump. Or another way of saying it is that the cost savings by using a vertical turbine pump against those other penalties is significant.
So I wish the answer to this is no, but the answer is yes. Does anyone else make a vertical turbine pump?
Yeah, like
I wish the answer was no, but no.
There are, other manufacturers that make vertical turbine pumps, but we're one of the few manufacturers that actually have a vertical turbine that's been pre-configured for this application. So that there's no guesswork. You don't have to figure out, we do all the engineering. You don't have to figure out how deep the hole has to be or how wide it has to be. We do that all for you. And you can actually have the can shipped ahead of the pump. So if someone needs to do the site work and the concrete pad out in the weather, we can actually ship the can and have that installed months before the pump would be available. And that's another benefit to doing this type of technology.
I mean, someone's asking if you could use a concrete sump instead. It might be a different application or pump, but that's.
Yeah, I mean, you could build a concrete vault or a sump if you want to go through that expense. Then you wouldn't use the canned version of the vertical turbine. You'd use a different version of a vertical turbine. But the reality is that the cost for medium-sized condenser water systems, open cell cooling towers for condenser water systems, we'll say medium-sized, again in the range between 1,000 and 1,500 tons in that order of magnitude. A vault would be pretty expensive.
So someone's asking this. So he was on a job site recently, and he's asking, are turbine pumps used for wells? I saw that recently at a job site. Obviously,
there
yeah.
are different styles and configuration of vertical turbines, and as Brett mentioned earlier, that market for those specialized pumps would be for the agricultural industry, used for irrigation, for mining, where they're dewatering deep mines, that sort of thing, and also for well, for applications where you have municipal applications, where you're trying to move a tremendous amount of water from point A to point B, like in a sewage plant.
That shaft you show there is arguably one of the shortest shafts on a vertical turbine pump. Usually they go a long ways down.
Yeah, I mean, what you're seeing here on the screen is specifically designed for open cell cooling tower condenser water systems. It solves a huge problem. We're taking what winds up being a very difficult problem to solve using conventional pumping and using a vertical turbine specifically designed for condenser water applications to solve major problems, and for a fraction of the cost of doing it differently.
Here's a great question, and we're getting close to the end here. Do the pumps self-drain for safe winterizing?
Generally speaking, the way the pump is set up is that it's below the frost line. So in other words, the bottom of the can is well below the frost line. So the water inside the can, you'd have to have I think it's in most states, I know in Massachusetts, the freeze table I think is at 4 feet below grade. So yeah, you may have to pump out a portion of the can, but as long as the water is below grade, you're not going to have a freezing problem. I mean, 4 feet below grade, not below grade, but 4 feet. And that varies, by the way, different parts of the country that are colder parts, that frost line can be deeper.
Any flow rate limitations? Any size limitations? Not really.
Not when it comes to cooling tower applications. I mean, you can buy chillers that are quite large, but let's say you went with a fairly large chiller, 2,000 tons, and that would be around 4,000 gallons per minute. Let's say you had 5 of those. So that would be 2,000 tons. Yeah, 4,000 gallons per minute. You would have 4 pumps at 4,000 gallons per minute each. And again, we can have any depth to accommodate the cooling tower physical arrangement.
Last question. Are these motors typically TFC?
They can be either TEFC or ODP, depending on the application and whether it's located physically inside or outside the building.
Well, you know what, Rich? One of your goals was to get this to be very interactive, and I think you accomplished that.
Yeah, hopefully we had enough questions. We probably should answer just one more before we call it quits. Got one more out there somewhere?
Someone says, I'm confused. How is the can 36 inches, but the depth is 10 to 20 feet? I don't know how that came about.
The can could be anywhere from 24 to 36 inches in diameter, and you would change the depth.
Yeah.
The depth of the can.
I think he misunderstood when you said diameter, and he thought he was thinking feet. You know what I mean? Yeah.
Yeah, 24 to 36 inches in diameter, and the can depth would be a function of what you need for net positive suction head. Because remember, the lower you make the suction of the pump, the greater the net positive suction head that's available. And that's really the problem you're trying to solve.
So Morgan is making a suggestion here, and I'm going to have to spell it because there's BITUMASTIC coating might be the right term for the can coating.
Bituminous.
But there you go. Well,
yes, I believe that's the correct term. I'm glad someone came up with that because I was struggling trying to remember the. It's a tar like. If you've ever seen, especially in New England, I'm from New England, when they build new homes, they pour concrete foundations so that you can have basement space, and before they do the backfill, they paint the foundation with the black bituminous material to keep it watertight. But it also, if it's coated on steel, it it lengthens the life expectancy of the steel can indefinitely.
Would you ever use something like this in a penthouse mechanical room, or is this only for grade level installation?
I mean, it's the good news and the bad news. If you had a cooling tower, let's say in a penthouse, and the tower wanted to be at the same elevation, the bottom of the tower wanted to be at the same elevation as the mechanical room, yes, you could use this to solve that problem for you. The beauty of the can turbine is it doesn't take up that much floor space, but it would extend into the floor below. So let's say you had a 10-story building, the roof was at the top of the 10th floor, and that's where your mechanical room was. Well, the can would have to extend down through the 10th floor and consume some space, but that could easily be disguised or hidden inside of a a building adjacent to a vertical shaft in the building, or left next to a men's room or ladies' room. It could easily be hidden so that nobody has any idea that there's a vertical can in their building. So yes, you can use it in buildings like that.
We're pretty much maxed out here, my friend.
Well, I want to take this opportunity to thank everyone for today's participation. Hopefully you got something out of this. And there's my minion friends are saying goodbye. So thanks a lot. And I'm going to turn it back to Brett.
So somebody's asking about when will we see the slides. Before I shut this down, there's a handout available that has all the slides. So go look for that handout. I won't shut it off right away and download it. It is Rich's presentation slide way. So keep
And
that in
then
mind.
the actual recording is available, what, roughly 24 hours?
Yep. And then tomorrow sometime you'll get a link to the recording and you can watch it and take pictures of every slide. But don't do us a favor. Don't design a system around any of these pictures.
Yeah,
Exactly.
these are for classroom only. And I will say that there may be people out in the audience that are saying, hey, you know what, this is an elegant solution to one of our problems. Contact your local TACO representative, and we'd be happy to come to your office and do a presentation, help you with the system layout. Just tell us what you need, and you should, give serious consideration to the vertical turbine condenser water solution. It's a very elegant solution. You may not have thought of it in the past, but you'll find that it's really kind of a slick way of dealing with a real difficult problem.
So one of our regulars here says, thank you guys for another interesting and fun webinar. You guys always keep it interesting. I guess that's a good comment.
That's that's like they used to say. That's a little colonial baloney from Colonial Baloney.
And our friend Darren up in Canada and our Julio in Texas says, thank you, great presentation. So anyways, quite a few thank yous. So anyways, Rich, great job as usual. And we're coming back. What month are we in? April? We got something in May. I think it's expansion tanks, another one of Rich's favorite subjects.
I love expansion tanks.
All right, guys, take care. See you, Rich. Bye, everybody.
Take care. Bye-bye.